workshop. Dear participants, good evening. I'm sharing my entire window. I would like to get a confirmation from your end, my voice audibility as well as my window visibility.
You're audible, sir, and it is
Yeah.
visible also, your screen.
Thank you. Thank you, madam. Yeah. Right. Today's session, the 2 day sessions, actually we have planned to cover 6 areas that it has been highlighted in the pamphlet of the workshop itself. Once again, I would like to share that the topics what we have planned to cover. My Word document, what I'm sharing with you is, I hope it's visible. Few participants, can you confirm the visibility of my Word document display at your screen? Few participants, at least one or two. If you are confirming, then again I will proceed further. Yes?
Yes, yes.
Right, okay. The first day, we have planned to cover 3 areas. That is the basics of statistics, descriptive statistics, exploring data. Especially among the 3, exploring data is a very, very important and crucial for any researcher. And tomorrow, we have planned to cover scales of measurement, sampling techniques, and inferential statistics, both parametric and non-parametric. Just I will give an overview how to choose or how to pick up a test. Rather than explaining how to conduct a test, I will help you to choose an appropriate test for a given scenario. Okay, with this objective, then again, I'm starting this session. So, once again, basics of statistics, descriptive statistics, exploring data is a today's topic we are planning. And tomorrow's topics, what we are planning is scales of measurement, sampling technique, and inferential statistics. That too, parametric and non-parametric. Here, our intention is not make you to are vulgarized in that particular working of the test rather than selecting a test. How can I choose an appropriate test for a given context? Okay, right. With that, I'm taking you to my PowerPoint presentation. I hope my PowerPoint presentation is now visible.
Yes, sir, it is.
Right, okay. Right. Dear friends, in our life, statistics is a part in every day and everybody's life. Without knowingly or with knowingly, we are applying the statistical techniques. Okay. And at the end of the session, so obviously, then again, you can understand the statement, what I am uttering it, whether it's true or not. Right. With that, then again, I'm starting with the basics of the statistics, about statistics. I hope all of you may aware about it. There is no need to talk much about that particular slide. What do you mean by statistics? It's very simply, we can say that it's a collection of data, organizing the data. Then from the organized data, we have to analyze it, we have to interpret it, we have to present the data. Every day we are doing it, irrespective of the profession. We are collecting some of the data, we are organizing the data, we are analyzing the data, we are interpreting the data, and finally we are presenting the data either to the top management or either among our colleague members. Right. With this small note about that particular statistics, I'm taking you to the branches of statistics. The statistics broadly that it has been classified into 2 areas: descriptive statistics, another one is an inferential statistics. I hope whenever we are talking about a population, the population here means the interest of our study or the objects on which we are interested to make an inference or a conclusions, whatever may be the words, we can use it appropriately. So when we are trying to describe a population, that it falls under the category of descriptive statistics. So, for example, let us take an Indian population. The entire Indian populations, when I'm trying to describe, I can use appropriate tools and then again I can describe it. That is fall under the category of descriptive statistics. Just here I'm describing, that's all, not more than that. And another branch of a statistics is called as an inferential statistics. That means I'm trying to make an inference about the population. I'm trying to make an inference about the population. I'm taking some of the samples and I'm trying to make an inference about the population. For example, let us take a blood test. In the human body, when we would like to talk about the blood, that entire blood in a human body is a population. The entire blood in the human body is a population. The entire population I can't study. I can't study. It's true. I can't study the entire blood. I can't take the entire blood of a human being and I can't test and then again I can't conclude. Normally, we are taking a 1 ml or a 2 ml of a blood from a human body. That is a sample. And with the help of the sample, we are trying to make an inference about the entire blood that is available in the human body. Whether the blood that it contains a hemoglobin as we suggested, or the platelets count, like blah blah blah. I can say all these things. So here, I am trying to make an inference about the population. One area of a statistics is describing the population. Another one is making an inference about the population by using a sample. Right. With this explanations, I'm taking two terminologies, population and sample. Population means any object you have intended to study. Any object you have intended to study. Say, for example, let us take Karnataka. From the state of Karnataka, I would like to study the entire engineering institutions. So my study that it constitutes a population, the engineering colleges situated in the Karnataka state, it's constitutes my population. What I am intending to study, that's all. Even you may intend to study the entire engineering colleges across India, that also you can take a population. But you have to decide the scope, right? Sometimes we are studying the entire population. Normally that is called as a census. We are called it as a census. But in all occasions, it is not possible. Why? Can you say, participants, come on, why we couldn't study the entire population? Why? With the common sense, then again we can give an answers. Come on, please come forward.
Extremely lengthy time, costly.
Yeah, timing, costly. You are saying that it's a cost involved. The cost involved, it's not bearable.
Yes.
And then again, second one is
Yes.
the timings. Yeah, beautifully. Then again, you have stated two reasons. Right. That is reason why normally we are taking a sample, a representative sample. I'm using that particular word, representative sample from the population, and we are trying to make an inference about the population, or we are trying to describe the population. If you are describing the population, that is called as a descriptive statistics. If you are making inference about the population, it's called as an inferential statistics. For that, there are two terminologies are very, very important. Understanding the terminology, sampling distribution, central limit theorem. There are two things are very, very important. My dear friends, in this session, I'm not covering the entire concepts. As a beginner of that particular research methodology, normally where the people will fall, where the people will struggle, where the people will stumble down in the understanding of the statistics, in the applications of the statistics, I'm picking up and then again I'm making a presentation. Rest of the things I'm leaving it to you for your own studies. Right. Let us now start with the sampling distribution and central limit theorem, my dear friends. My pace of the delivery is okay, good. Could you now follow with me, or shall I slow down my presentation?
Yes, sir, it's
No, sir,
fine.
this is fine.
Right, okay. Now I'm coming to the sampling distribution. In the sampling distribution, see here, this is my population. In the top, this is my population. The big oval shape is a population. This is my interest of my study. That mu, symbol mu here, can you see my pointer? Mu equal to 3. That means the mean value or the average values are 3. As you rightly pointed out, I can't study the entire population because of the timing, because of the cost, etc., etc. Right. For that reason, we are taking a sample. Let us take a sample. This is a sample 1. This is a sample 1. This is a sample 2. 1 minute. Then again, I will take up a pen and then again, so that easily then again I can point out also. 1 minute. I will take the pen and then again 1 minute. Right. Just a minute. I would like to use a pen appropriately so that then again you can get the inputs properly. Crashes. Right, okay. Let us now start with this one and then again. I am using the pen here itself. Okay. So this is a sample number 1. This is sample number 2. And this is a sample number 3. And this is a sample number 4. And this is sample number 5. And this is 6. And this is 7. And this is 8. And this is 9. There are 9 samples. Any one of the samples I can take up. Any one of the samples I can take up. Is it right? See, if I'm asking you to take a sample from this population, you can take a sample. Somebody, if I'm asking them to take a sample, they may take a sample. Each and every sample have its own mean value. See here, the mean value has been given here. The first mean value is x bar equal to 3. The second mean value of the sample is 2. The third sample mean values are 4. The fourth sample mean values are 3. And fifth sample mean values are 1. 6 to 1, 4, 7 to 1, 3, 8 to 1, 5, 9 to 1, 2. Like from each and every sample, I may have a different mean. When you are populating this sample mean, see here at the bottom of the diagram, I have populated here. How many times the sample carries an average of 1? How many times the sample have an average of 2, average of 3, average of 4, average of 5. That interval tends to normally distribute. See, here I can take n number of samples. For example, here I took 9 samples. Any number of samples you can take. But here for an example, I'm taking 9 samples. If the 9 samples mean value when I'm populating, the histogram will look like this. That it will tend to normally distributed data. So the mean of all the means, see the first mean 3 plus 2, 5, 5 plus 4, 9, 9 plus 3, 12, 12 plus 1, 13, 19, 22, 24, 29, 29 divided by 9. Like I can divide it, then again I can take a mean. Actually it's a 27. So the mean values are 3. See, if the sample means are tend to normally distributed. So the distribution of the sample means, the histogram, what that it has been shown here is a sampling distribution. The sampling distribution always tend to normality. That is a central limit theorem says. Based on that assumptions only, I can leverage the samples, what I have drawn it from the population. Using that, I'm trying to make an inference about the population. I'm describing the population. All of you are comfortable, please tell me. Otherwise, then again, I will once again repeat. Can you now imagine and visualize what do you mean by sampling distribution?
Yes,
Sampling
sir.
distribution is a n number of samples you can draw from the population. Each population may have a mean value. When you are plotting the mean value of all the samples drawn from the populations will tend to normality. So the tending to normality is a central limit theorem. All the samples means what that it has been distributed here is called as a sampling. Clear? Once again, I will repeat whatever the doubts I will clarify here. Because without a proper understanding of this, you can't learn the statistics.
It's
I
clear.
think it's a clear, right? Well, few more people, can you say? So that then again I will move further. The learning here is population, sample, sampling distribution, central limit theorem. Beginning, we started with what do you mean by statistics? It's a collection of data, organizing data, analyzing the data, and interpreting the data and presenting the data. There are 5 major components in the statistics. Okay, clear now?
Yes, sir.
Right. Now, this central limit theorem says that, see here, the mu value that it represents the population mean. This mu is representing the population mean. The x bar that it represents the sample mean. X double bar represents the sampling distribution mean. Sampling distribution mean. Both are equal. What the theorem says? The central limit theorem says x double bar equal to x bar equal to mu. Can you now understand what is an x double bar, x bar and mu? Mu represents population mean, x bar represents sample mean, x double bar indicates
Combined.
sampling distribution mean.
Combined.
Sampling distribution mean. That is a n number of samples mean. N number of samples mean. Okay. Yes or no? The first mean, what I have stated based on the central limit theorem, all of you are comfortable?
Yes, sir.
Right. Now I am coming to the second one. In the second one, it's a tricky standard deviation. I hope all of you are comfortable with the word it's standard deviation. Variance, standard deviation, coefficient of variance. I hope all of you are comfortable with this terminology. With that assumptions, I am taking you to the next level. The standard error is nothing but the standard deviation of the sampling distribution. The standard deviation of the STD, the standard deviation of the sampling distribution. Are you comfortable? Error?
Yes.
Standard error is nothing but a standard deviation. Which is standard deviation? Sampling distribution standard deviation. Sampling distribution standard deviation. Okay, all of you are comfortable?
Yes, sir.
Yeah.
Somebody is asking to repeat the previous point.
Yeah, I will repeat that
Oh.
one. See, what is the first sample mean?
It refers to the mean of one sample.
The first sample mean is how much?
It is 3.
3. Second sample mean?
It is 2.
2. Right. Now, I'm taking all the samples and its means. The mean of mean value. The total is 27. All the sample mean value is 27. How many samples are there? 9. So, what is the mean? 3 is the mean value. This is a mean of mean. This is nothing but x double bar. X double bar is nothing but 3, this 3 plus 2, 5, 5 plus 4, 9, 9 plus 3, 12, 1, 13, 17, 20, 22, and 27. The total mean of all the samples is 27. How many samples are there? 9 samples are there. So 27 divided by 9 is a 3. That is nothing but x double bar. This is x double bar. Are you comfortable now?
Yes, sir.
What is the central limit theorem says? X double bar equal to x
Analysis.
bar equal to mu. What is a mu? Mu is nothing but population
Mean of the
mean. X bar means what? A single sample mean. What do you mean by x double bar? Sampling distribution mean. Comfortable with this all notations and terminology? The mu represents population mean. This is a population. See here, this is a population. This is the entire population. What does the entire population mean? 3. Okay. X bar means what? The sample mean. Okay. What do you mean by x double bar? All the samplings mean value. How I am calculating x double bar? Each and every samples, if I am taking from the population, each and every sample may have a mean value. If all the mean of mean, that is called as a x double bar. Okay, all of you are comfortable?
Yes, sir.
Right, okay. Now, I have to calculate the standard error. How can I calculate the standard error? See here, I have to take the first sample mean. What is the first sample mean? 3 minus x double bar. I have
3.
to take, and I have to whole square it. Plus, I have to take the next one. What is the next sample? X bar 2. That is the second sample, 2. I have to subtract. I have to subtract the value from the grand mean. That is a standard distribution mean. That it has to be square. Plus, next one, like I have to keep on go up to n number of samples. So this sum of these values divided by n will give a standard error. Standard error. That is a square root of this value is called as a standard error. See here, this is a standard error. Standard error is nothing but sampling distribution standard deviation. All of you are comfortable?
Yes, sir.
Right. In practical world, can I take a n number of samples? Can I ensure that it is normally distributed and all the properties, can I use it for statistics? No, it is not possible. Again, it is a time consuming. Again, it is a cost involved. So the central limit theorem says that the standard error can be calculated by sigma divided by root n. Sigma divided by root n. What is a sigma? Sigma is nothing but population standard deviation. Population standard deviation. Population standard deviation is called as a sigma. Sigma divided by root n is it represents the standard error. Or suppose I'm not aware about the population standard deviation. I'm having only a sample standard deviation. Yes, that is a small s. This is a sample standard deviation. This is a sample standard deviation. When I'm having a sample standard deviation, that can also be divided by root n. So this is equivalent to what, my dear friends? Standard error. Standard error is nothing but sampling distribution standard deviation. Okay? Which theorem that it says? The central limit theorem says that the mean equal to x double bar equal to x bar equal to mu. Standard error equal to sigma divided by root n or s divided by root n. Okay? All of you are comfortable? All of you are comfortable? Sir, why we have to bother about sampling distribution? You may ask a question. But what is our purpose? Taking a one sample and we are trying to make an inference about the population. Is it appropriate? Yes, the central limit theorem says it is an appropriate. We can apply. And what is the thing that is required? That thing required is mean value and standard errors are required for making such a kind of an inference. Right. I'm stopping my lecture now. Please tell me if you are much comfortable, say yes, or otherwise say no comfortably. I will repeat once again, because Normally, the people are lagging in this particular understanding. Without understanding this, we are trying to learn the remaining part of the statistics. Obviously, we are struggling. Can you now understand this one? Here, I'm removing all my inks. 1 minute. I'm erasing all my inks. So this is a population. From the population, we are taking n number of samples. Each sample have a mean value. If you are plotting all the samples mean value, always that it will tend what, my dear friends? Always that it will tend normal distribution. Normal distribution. Because it's normally distributed, I'm trying to make an inference about the population. See, one thing, then again, you can ask a question. Sir, how can you draw some samples and how can you talk about the population? Is it appropriate? Yes, the central limit theorem says it's inappropriate. Yes, we can make an inference about the population by using the sample. They have proved it also. All of you are comfortable? Tell me, or otherwise, once again, I will repeat. All of you are comfortable with the terminology population, sample, sampling distribution mean, standard error.
Yes, sir.
Right. Don't hesitate. Here we have assembled only for learning purpose. And if you are not comfortable, please tell me ruthlessly, sir, I couldn't follow you. I couldn't follow with your words. Once again, I will repeat with other words so that you may try to understand. Right? Shall we
So
move further?
standard error, could you just repeat once again, please?
The standard error is nothing but the standard deviation of sampling distribution. Are you comfortable with the word sampling distribution?
Yes, sir.
That sampling distribution standard deviation is called as a standard error. Whenever you are hearing that particular word standard error, immediately you have to understand that we are talking about the standard deviation of the sampling distribution.
Okay, sir.
And what is the sampling distribution? See here, from a population, you can take n number of samples. All are possible. So, for example, I'm asking you to take a sample from your class. You're taking some sample of students. You are asking me to take a sample. I can take a 4 students. You can also take some other samples. So each and everybody can draw a different kind of a samples with the permutation combinations. Each and every sample have a mean value. If all the samples means, if you are plotting, always that it will tend to normality. It's approved. Even you can also check. And all these samples mean are how far it is deviated from the x double bar. How I am measuring the dispersion? X bar 1 minus x double bar whole square. I am finding out the deviation. Plus second observation. What is the second observation? Second sample mean. What is the second sample mean? X bar second sample minus x double bar whole square. Plus, like I'm moving to n number of samples. And the summation has to be divided by n, that it will give the variance. When you are taking the square root, that it will give a standard deviation. That standard deviation is called as standard error. Could you now get the point?
Yes, sir.
Right. Now the question is, sir, how can I take for 100 samples? How can I calculate the mean of all the 100 samples? How can I measure the variance? It's a tedious job once again. Instead of that, I can study the entire population. You may ask a question. For that reason, central limit theorem says that there is no need to take a number of samples. Take one sample, more than sufficient. Calculate the variance and calculate the standard deviation divided by root n. The n is nothing but sample size. Your sample size, say for example 100. Okay, your sample standard deviation is, say for example, it is a 10. Your standard deviation is 0.01. Do you now understand? My sample, I'm taking only one sample. The one sample standard deviation is how much? 10. Then again, the square root of n is 100. So for example, you are taking how many samples? 10,000 samples you are taking it. Square root of 10,000 is how much? 100. So 10 divided by 100, how much? 0.01. The 0.01 is nothing but it's a standard error. What is the standard error? The standard deviation of sampling distribution. It's equivalent to take 10,000 samples and calculating the standard deviation. It's equivalent to that one. Could you now understand?
Yes, sir.
Right, okay. Shall we proceed further?
Yes.
In another slide, I'm showcasing the notation that it has been used for population, the notation that it has been used for sample. Wherever you are seeing that notations, you can understand that whether that it talks about the sample or a population. The population parameters, the population is normally called as a parameter and the sample that's called as a statistic, not statistics. Not statistics. Yes, there is no S, only statistic. The population is termed by parameter. Population parameters. Sample statistic. Could you understand the words? What is associated with that one? S? Yes or no?
Yes, sir.
Right. Now, the mean of the population is denoted by mu. X bar is used to denote the sample mean. The proportion, pi represents the population. The small p represents the sample. Variance, sigma square represents the population. Small s square represents the sample. Standard deviation, sigma represents the standard deviation. Small s represents the sample standard deviation. Size of the objects. Capital N indicates population. Small n indicates the sample. Sigma sub x bar. This is sigma sub x bar actually. Sigma sub x bar. It's a standard error of the mean. Standard error of the mean. That is nothing but sigma divided by root n. Can you remember what we have seen in the previous one? Sigma divided by root n. Can you see? This is called as what? Standard error. The standard error notation is sigma sub x bar. And this is a small s divided by root n. Small s divided by root n. This is denoted by s sub x bar. Sub means subscript. In the subscript, not superscript, in the subscripts. Okay? Like similarly, standard error of the proportion, sigma sub p, s sub p, that is a standard error of the proportion. Standardized variance, this is, ignore it. These two things, then again, later point of time we can see. See, these are all the notations. Based on that, you can understand whether that it has been talked about a population or a sample. Is it okay, my dear friends? Is it okay?
Yes, sir.
Right. Now, I'm moving to the next critical point that is called as an arrangement of data. Right. So far, what we have learned, once just then again, I would like to summarize. We have learned about statistics. It's a collection, organizing the data, analyzing the data, interpreting the data, and presenting the data. There are 5 components in the statistics. Statistics have 2 branches: descriptive statistics, inferential statistics. Descriptive statistics describe the population. Inferential statistics make an inference about the population. Population means the object what we are intending to study. Whatever may be, we have to define the scope. Sample means what I am drawing some of the objects from the population for making inference about the sampling distribution and central limit theorem we have studied. Sampling distribution always tend to normality. And sampling distribution mean is nothing but x double bar is equal to x bar equal to mu. Standard error is nothing but standard deviation of the standard sampling distribution. That is a sigma divided by root n or small s divided by root n. That it has been described by the central limit theorem. Right. These are all the notations. Right? Right. My dear friends, Here, 1 minute. 1 minute. I have done a small mistake here. Yeah. Always, then again, I'm making small mistakes. 1 minute. Okay, right. This is an arrangement of data. This is an arrangement of data. Arrangement of data. See, I'm taking some of the machine's details or the output, output products diameter. Imagine piston diameter. Imagine from the machine one, what are all the pistons diameter I have measured? I am presenting it in the columnar data. This type of a structure is called as unstacked data. This is called as a unstacked data. The same set of data has been represented by two columns. Namely, machine is a one column, value in another column. See, machine 1 value 0.1247. See here, this one. This one has been denoted. See here, this value has been shown here. Okay. And what is the second value? This is the second value, 2.16. Like all these values up to 1.254. The first machine up to 1.254. The value that it has been denoted here. Thereafter, I'm starting with the second one. All the second machines, all the third machines, like I have shown here. This is called as a stacked data. This is called as a stacked data. Okay. Just I'm trying to make you to visualize. Okay. Can you observe the two pattern of the data sets, what that has been presented here? Here, each machine has been shown as a separate column. Even it is a 10 machines, 10 columns we are showing the values. Normally, we are presenting the data in such a fashion. Always we are showing the data in a stacked data. But this, unstacked data. This unstacked data can be shown like this. Machine as a one column, value as an another column. Right? With the small example, I'm taking you to the next exercise. Okay. 1 minute. I'm showcasing a value here. Can you now see my Excel sheet?
Yes.
Right, okay. I hope all of you are comfortable with this one. Roll number, name, subject code. This is a subject code. 10 MB 11, 10 MB 12, 10 MB 13. Like there are n number of subjects of the program, MBA program. Okay. And all the values are all marks. Okay. Normally we are presenting the data in such a fashion. Is it right, my dear friends? Now,
Yes, yes.
from the example, what you have seen from the PPT, can you say that whether it is a unstacked data or a stacked data? Just to try it, right or wrong, don't bother.
Stacked data.
Stacked data, right. I'm taking you to the next slide. See here, stacked data. This is a stacked data. Sir, can you see? This is a stacked data. Stacked data contains machines as a one column, values as another column. But unstacked data have each and every column have a machine 1 data, machine 2 data, machine 3 data, like that it goes. Like now I'm taking you here. Here we are taking subject 1, subject 2, subject 3, subject 4, subject 5, like n number of subjects I am showing it. Can you map it, whether it is an unstacked data or a stacked data?
Data.
Unstacked.
Unstacked data. Very good. Unstacked data. Because each and every subject has been shown in columnar. Is it right? See, I'm showcasing in another one. See here now, tell me. Roll number, name, subject code, and marks. Can you associate this one? I will take you here, like 1 minute. Can you see side by side? 1 minute. I will take my PPT. Can you see side by side? Can you see side by side, and then again, can you see?
Yes, sir.
Yes, sir.
Right, okay. So what kind of data arrangements? It's
Unstacked.
It is stacked.
Stacked
It is
data.
stacked data because subject is a one code, subject is a one column, and mark is an another column. Right. Now you may ask a question, sir, right? You are now comparing these two, and then again you are asking us whether it's a unstacked data or a stacked data. We are capable enough to say, but how we can come to a conclusion when a new set of data that has been given to us. Now you can ask a question, right? There is a one rule of thumb. Please make a note of it. It's very, very important. Number of variables equal to number of columns. Number of variables equal to number of columns. What is the rule that it says? Rule of thumb says. Once again, I will write down also. Okay. So number of variables equal to number of variables equal to number of columns. Okay. Number of columns. My handwriting is a little bit poor. So again, with the mouse I am using to write down, so I am not using the pen. Epic pen is not working in my, I don't know why. So I am struggling with that one. So number of variables equal to number of columns. This is the rule of thumb. Always keep it in your mind. Whenever you are seeing the data, you have to ask a question, whether it is a stacked data or an unstacked data, because arrangement of the data is very, 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 very important for statistical analysis. Normally, the people are struggling to understand, right? Now, my dear friends, let us take unstacked data. In this data, what are all the variables are there? Can you identify? This is a piston diameter. Imagine the values are piston diameters. So please, can you tell me how many variables are there in the unstacked data table? Identify, come on.
3 variables.
3 variables. What are all the 3 variables?
Machine 1, machine 2, machine 3.
No, madam. Machine is a one variable. Machine is a one variable. That's all. Machine number 1, machine number 2, machine number 3 is the n number of machines. That's all. Machine is a one variable. That's all. So machine 1, machine 2, machine 3 is not a variable. Machine is a one variable. Right. What else? Come on. What else? Come on. What else? What is the remaining part? The machine 1, machine 2, all the 3 machines belongs to machine variable. Is it right? That is the first variable. Right. What about the remaining values? These values are all what, my dear friends? These values are all what? Piston diameter? Yes?
Yes, sir.
Yeah.
So the piston diameter, normally we may call it as a value, piston value. The piston dia value is another variable, that is a second variable. How many variables are there in this table? There are 2 variables are there. When I am stating that for a stacked data, what is the rule? Number of variables equal to number of columns. If the number of variables is not equal to not columns, that is an unstacked data. It is not equal unstacked data. It is an equal stacked data. Is it okay, my dear friends? Is it okay?
Yes, sir.
Yes, sir.
Right, okay. Now I am taking you to our example. Now let us cross check. Okay, in the Excel sheet. Here, my dear friends, tell me how many variables are there in this Excel sheet. It's a known data. It's not that much of a difficult data set. It's a known data set. So the 10 MB 11 are all already I stated that it's a subject code. Is it right? These are all the subject codes. The values are all nothing but it's a marks, and this is a student name, and this is a roll number. Come on, tell me what are all the variables are there. Now let us count. Come on, come on, come on.
Roll number is a variable.
Yeah, 1 is a roll number. Come on.
Names is the variable.
Second, name is another variable. Come
And all
on.
the subject codes marks are variables.
Yeah, subject code is a variable.
Code is a variable.
Subject code variable.
Subject code is a variable. Then mark is a variable.
Variable.
How many variables are there?
Totally
3.
1, 2, 3, 3,
Four.
3, 4.
4. Roll number, name, subject code, marks. Okay? Okay, guys?
Yes, sir.
If the number of variables equal to 4, how many columns supposed to be in order to have a stacked data?
4.
4. See, here how many columns are there? More than 4? Yes or no?
Yes, sir.
So this particular data set is called as what, my dear friends? number of variables not equal to number of columns. So this data set is called as what, my dear friends?
Unstacked data.
Unstacked data. Very good. That's all. Now I'm taking you to the next one. Here. Now tell me, how many variables are there? 4. How many columns are there?
4.
4. Both are equal.
Yes, sir.
Right. This type of data arrangement is called what?
Stacked data.
Stacked data. That's all. Please practice. Please be well versed. Whenever you are seeing the data set, any data set, that's maybe a mark statements or an attendance percentage or any sales data or a financial data, whatever may be. As soon as you are seeing the data in a tabular format, please count the variables. How many variables are there? How many columns are there? Both are equal. You can conclude that that is a stacked data. Stacking means arranging one above the another one above the another one. See, the first subject 11, subject code 11 is arranged first. See here, all the students subject, the code 11 arranged, and thereafter what is arranged? Subject 12, 10 MB 12. Like a subject above which a subject and above which a subjects are arranged one after another, one above the another, that it has been arranged. That is reason why it is called as a stacked data. Stacking means keeping one above the another one is called as a stacking. Could you now understand the meaning of stacked data and stacked data?
Yes, sir.
Yeah, this is
Yes, sir.
also very, very important as far as that particular statistical analysis is concerned, because whenever we are using a software, we may use a SPSS or MinTab or even in Excel, okay, or whatever may be the package, that may be an R programming or a Python, whatever may be, the arrangement of the data set is very, 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 very important. Now you may ask a question, sir, between the two, which is preferable? Stacked data is always preferable. Stacked data is always preferable. Okay, guys, please make a note of it. Always we have to prefer the stacked data rather than the unstacked data. Unstacked data is in report format. Stacked data is meant for analysis purpose. All of you are comfortable or not comfortable?
Yes, sir.
Comfortable, sir.
Right. Shall we now move the next level?
Yes, sir.
Yeah. In the descriptive statistics, my dear friend, when we are talking about the descriptive statistics, there are 4 things. First order business movement, second order business movement, third order business movement, fourth order business movement. I can using it with a different name, measures of central tendency, dispersion, skewness, kurtosis, like I can call. These 4 things is required to describe any population. Either you can use sample, but the sample with which you have to try to describe a population. So what are the tool you can use it? Measures of central tendency. What do you mean by measures of central tendency? First order business movement. Dispersion, how the data that it has been dispersed from the central point or a mean value or an average value is called as a dispersion. That is a second order movement, business movement. Skewness and kurtosis. Okay, right. Now let us first move to the measures of central tendency. I hope all of you are comfortable with this measures of central tendency. Mean, median, mode, geometric mean, harmonic mean. There are 5 measures of central tendency. We are using it. Okay, my dear friends? Yes or no?
Yes, sir.
Yes, sir.
Now you may ask a question. Sir, when can I apply mean? When can I apply median? When can I apply mode? For that, I'm taking you to the another slide. Wait a minute. I'm taking you to another slide. I will showcase the measures of central tendency. The measures of central tendency itself is a very powerful tool in statistics, provided appropriately you are using it with an appropriate understanding. Okay, I'm taking you to the slide. Wait a minute. Yeah, can you see the new PowerPoint slides presentation? Yes?
Yes, sir.
Yes, sir.
Okay, cool. Right. See, my dear friends, quickly I can say arithmetic mean is very simple. Whenever there is a summation process happens, you can apply arithmetic mean. Okay? The arithmetic mean is simply the sum of the values divided by number of observations. Sum of value divided by number of observations. Right. Already we are applying the mean very often. We are summing up the value, we are divided by number of observations. It's very easy. But when can I apply median? The median is a one when there is an outliers, or when we would like to point out the middle point. Say, for example, my dear friends, extreme values. So say, let us take salary. In the CEO of the salary of a company will be very, very high. It's a crores and crores. But the average of the middle management, the salary of the middle management, the salary of the bottom management are moderate. At the time when I am considering the COE value or salary value, that it will distort. I have to take up at that point of time, I have to take up the median only, the midpoint. The midpoint. Whenever there is an outliers, whenever there is an extreme values are there, I have to apply median. Okay, right. So the median for which we have to arrange the data and we have to find out the central point or midpoint, right? So the next one is a mode. The mode is one when we are talking about a qualitative data. When we are talking about a qualitative data, we have to apply mode. Most frequently occurred, or most popular. Okay, say for example, when we are talking about a cinema, the name or the cinema or the actress or actor or hero, or whatever may be. So all are qualitative in nature. Text values, when we are talking about the text values, we have to go ahead with the mode. When there is a numeric value, we have to go ahead with the mean. And when there is an outliers, I have to go ahead with the median. When there is an outlier, meaning extreme values. When there is an extreme values in my data set. Example is a salary. CEO of the salary is very high, comparatively speaking about the medium and the low level management salary. Right. Coming to the geometric mean, whenever there is a multiplication applies, you have to go ahead with the geometric mean. So for example, one example I can say, what is a rectangular or the square area? How can you calculate the area of the square? I hope all of you can comfortably say square. Area of the square?
Side square.
Side by side? Normally, are you multiplying or are you adding?
Multiplying.
Multiplying. That's all. It's very simple. Whenever there is a multiplication applies, when you would like to calculate the average, then again size of the rectangular or size of the square, you have to apply a geometric mean. In financial data, whenever you are calculating the growth, obviously you are multiplying the values. At the time you have to apply geometric mean. So very simple. Keep it in your mind. Plus is involved means mean. When there is an extreme value, median. When there is a qualitative data, mode. When there is a multiplication of values, geometric mean. The next one is a harmonic mean. The harmonic mean is when the two values are inversely related. Speed and distance coverage. If the speed increases, the time of the coverage of the distance whether will come down or that will goes up. The speed increases, the time of the travel will goes up or comes down.
Comes down, sir.
Yeah, whenever the two variables you are talking about are having an inversely related, At the time you have to apply harmonic mean. At the time you have to apply harmonic mean. Okay. So I'm not going detail about the calculations and all of the things. My purpose of this showing the slide is when you have to apply the harmonic mean, geometric mean, median, mode, and simple mean or arithmetic mean. All of you have got an idea? When can you apply harmonic mean? When the two variables interested are inversely related. Inversely related. Okay. So, for example, manpower and completion of work. If the more number of manpowers, number of days to complete the work will come down, or that goes up. The number of employees and the time duration to complete the work. More number of employees, less number of hours. More number of employees, less number of hours. Inversely related. One is goes up, another one will come down. If the number of employee goes up, the duration of the work will come down. The total duration required will come down. If the speed increases, the time to travel will come down. Inversely related. Whenever the two variables are inversely related, then again you have to apply harmonic mean. Whenever there is a multiplication process, you have to apply geometric mean. Whenever there is a qualitative data, you have to apply mode. Whenever there is a extreme values, you have to apply median. When you are having an additive values, when you are summing up the values without any extreme, without any qualitative data, you have to apply arithmetic mean, simple mean. I hope I have justified, especially in the application of measures of central tendency. I hope all of you are comfortable.
Yes, so very clear.
Very clear. Right. See, how to calculate, that is your job to learn. I'm not teaching you how to calculate the mean, median, mode. Please learn. There are a number of books are there. But where normally we are struggling, when can I apply mean? When can I apply median? When can I apply geometric mean? When can I apply a harmonic mean? Okay. That is the one, then again we have to learn really. That is a crux. Right. Now I am moving to the measures of dispersion. In the measures of dispersion, the first one is a range. Range is nothing but, my dear friend, maximum minus minimum. It's a very simple and straightforward measures of dispersion. What is the maximum? What is the minimum? The difference is called as a range. I hope all of you are comfortable with the variance. Already I have talked about it. Sum of x bar, x minus x bar, okay, whole square. Okay, this is a sum of, okay, divided by n will give a variance. When you are taking the square root of the variance, it's called as a standard deviation. The standard deviation is an absolute measure. Absolute measure. The coefficient of variation is a relative measure. Relative measure. The coefficient of variation is nothing but, okay, sigma divided by x bar. Sigma divided by x bar is a formula. Right. What do you mean by absolute measure? What do you mean by relative measure? I will explain with a small example. There are two students. One student has secured 800 marks. Another student has secured 400 marks. Student A secured 800. Student B secured 400. Who has performed better? Who has performed better? My dear friends, come on, tell me.
B.
800 or 400? 800. Very good. Now, I'm adding a furthermore information. The student A has secured 800 marks out of 1200. The student B has secured 400 marks out of 500. Which student is better now? Tell me.
B, sir. 400 out of 500.
Yeah. A couple of minutes back, somebody says that it's a is a better, 800 is a better, but now you are saying that it's a 400 is a better. Why? Why such a kind of a confusion?
Because of the percentage, both seem to be the same.
Yeah. When we are comparing the marks secured with the total marks. Is that right, my dear friends? So the 400, 800, what I have stated is called as an absolute measure. What I have stated as a 400, 800, what I have stated is called as what, my dear friends? Absolute measure. The relative measure is nothing but 400 out of 400. Out of how many marks he got 400? Out of 500, he got 400. Out of 1200, how many mark he got it? The first guy, 1200. Out of 1200, 800 marks he has secured. See here, I'm comparing the value with the total marks here. The marks secured divided by the total marks. This is called as a relative measure. Like the standard deviation, what we are calculating is an absolute measure. Sometimes that it may help, sometimes that it may not help. Okay, are you clear now? Among between the two, absolute measure and relative measure, which is a better one? Which is the better one?
Relative.
Relative measure is a better one, right? Okay, it's a straightforward conclusion. Now I am giving in one more scenario. You are having two options. Option number one is company A provides 20% of return. Company B provides 80% of return. Which one you will prefer? You are having a choice. Company A, how much that it provides a return? 20% return. Company B gives a return of 80%. Which one you will prefer?
Is there any additional information or this is entire?
Yeah, without that one, which one you will prefer?
Without any additional information, of course, B.
The 80% return, right? As you rightly asked, then again I'm giving an additional information. The 20% return is nothing but the ACC Cements. They are having a turnover of 200 crores, and the company B is nothing but it's a mango wala. He is making a business in the beach. He is making a business of 5,000. Which one is better now?
Just 5,000 rupees.
5,000 rupees.
Okay.
The ACC Cements makes a business of 200 crores and the Mango Wala make a business of 5,000. Now tell me which one then again you will prefer? A. See, sometimes then again without any information you have preferred B, but now you are preferring A. Why such a kind of a confusion?
So it's not a confusion. Additional,
Right,
additional information gives clarification.
Right, okay. And before this one, then again, after the explanations of the absolute measure and relative measures, what we have concluded? Relative measure is a
better one.
But 80%, 20% is a relative measure that's supposed to be a better. Why now it's a confusion?
20% of 200.
Yeah. See,
80% of 5,000. There's a big difference.
Very good, very good. See, whenever we are having it, we should have both the measures together to come to a conclusion. Simply, you are not supposed to stick with the relative measure. Simply, you are not supposed to stick with an absolute measure. Whenever there is an absolute measure, you have to ask for a relative measure. Whenever there is a relative measure, you have to ask for an absolute measure. Then only you have to come to a valuable conclusion or a valid conclusion. Are you comfortable now?
Yes, sir.
Right. So the standard deviation is an absolute measure. Coefficient of variation is a relative measure. What is a relative measure? The relative measure is nothing but sigma divided by x bar. Sigma divided by x bar. Okay. Sigma divided by x bar. Right. Now, my dear friends, whenever we are dividing the two values, you are getting a results. Whenever you are dividing a values, you are getting a results. Is it right, my dear friends? Whenever you are dividing values, we are getting a results. Now, the result is related to numerators. Always the denominator is 1 or 100. This is related to denominator. When I am dividing the sigma divided by x bar, I have to interpret the results. For a one mean, how much standard deviation? For a one mean, how much standard deviation? For 100% of the mean, what is the standard deviation? That way I have to interpret it. In any relative measures, whenever you are dividing the value, the result is related to the numerator, the denominator is always 1 or 100. If you are talking about a percentage, 100. If it is a decimals, you have to talk about 1. For a 1 mean, what is a standard deviation? That is a relative measure. For a total standard deviation, absolute measure. Can you now comfortable with this?
So please repeat this.
Once again, I'm repeating. Any two values, say for example, let us take profit divided by sales.
Okay.
Profit divided by sales. You are having a profit of 10 rupee and sale of 100 rupees. What is the value? What is the result here? 0.1 or 10 percentage?
Yes, sir.
This 0.1 related to what? Numerator.
Okay.
The denominator is always 1. Meaning, for a 1 rupee of a sale, how much profit you are getting it? 10 paise of a profit you are getting it. For a 100 rupee of a sale, how much you are getting a profit? 10 rupee of a profit you are getting it. So whenever you are dividing the values, two values, the result is always related to numerator. The denominator is always 1 or 100. If it is a percentage, we have to interpret. Can you now catch the point?
Yes, sir.
Right? So similarly, here the coefficient of variation. Coefficient of variation is nothing but what does it mean? Relative measure. What is the relative measure? Sigma divided by x bar. Now, sigma divided by x bar means, say for example, sigma divided by x bar. This is the value. The value is 2. Imagine 2. The 2 is related to what, my dear friends? The 2 is related to what? The 2 is related to numerator. What is the numerator here? What is the numerator here?
Sigma. Standard deviation.
Standard deviation. This is called as a coefficient of variation. The coefficient of variation is equal to sigma divided by x bar. Okay? Sigma divided by x bar. Sigma divided by x bar, the values, assume that it's a 2.
Okay.
This is related to numerator.
Numerator.
And what is the denominator value?
X mean.
The denominator value 1. The denominator value 1 represents x bar. Is it right? For a 1 mean, how much standard deviation? 2 standard deviation.
2.
That is an interpretation. For a mean value, 2 standard deviation. Suppose here it is a 5, standard deviation is 5. And what is the denominator? 1. For a 1 mean, 5 standard deviation. Is it right, my dear friends? When you are comparing the values with the different magnitudes, you have to always go ahead with the relative measure. You have to always go ahead with the relative measure. Okay, sir? Whenever there is a magnitude differs, you have to go ahead with the relative measure. But whenever you are taking a decision, always you have to consider both absolute measure and relative measure. Is it okay now, my dear friends?
Yes, sir.
Right. So what are all the measures of dispersion? Range. Range is nothing but maximum minus minimum. The minimum, the variance is a 1. We are calculating, but mostly we are not using the variance because it's a squared value. It's a squared value. Standard deviation is an absolute measure. Absolute measure. Coefficient of variation is a relative measure. Right? Up to this, what we have seen is a single variable. When we are talking about two variables, we have to call it as a covariance. When we are talking about the two variables, what is the measure of dispersion? Up to this, range, variance, standard deviation, coefficient of variations. All the 4 are related to what? One variable. Suppose if it is a 2 variables, what do you have to calculate?
Covariance.
Covariance or
The
correlation.
covariance is an absolute measure. The standardized measure is called as the relative measure is called as a correlation. The relative measure is a correlation. The standardized covariance is called as a correlation, or the relative measure of the covariance is called as a correlation. Are you comfortable now?
Yes, sir.
Right. For a one variable, measures of dispersions, what are all the measures of dispersions you can calculate? Range, variance, standard deviation, coefficient of variance. Standard deviation is an absolute measure. Coefficient of variance is a relative measure. Right. All the four related to or talks about one variable. For one variable, you can apply variance. For one variable, you can apply standard deviation, coefficient of variance. Suppose if you are interested with the two variables, you have to go with the covariance. So, for example, you are talking about only one subject, Tamil or English. If you are taking English, you can apply range, you can apply variance, you can apply standard deviation, you can apply coefficient of variance. But when you would like to compare English and science, two subjects, when you would like to talk about it, how can you measure the dispersion? Covariance you have to apply. The covariance is an absolute measure. Correlation is a relative measure. Now I am stopping my lecture. Please tell me now, are you comfortable or not?
Yes, sir.
If you are not any doubt, then again let us move further. Yes or no?
No doubt, sir.
Now I am moving to skewness. Skewness, I will first showcase the diagram. Thereafter, I will come to the theory part. This particular diagram shows that it's a left skewed or it's a negatively skewed data. This is called as a negatively skewed data. And this diagram shows that it's a right skewed data or it's a positively skewed data. This is a symmetric, means there is no skewness. There is no skewness. Okay, there is no skewness. Okay, can you now understand the three diagrams? Right. Let us now take the example of a marks. Don't bother about Q1, Q2, Q3, the bottom figures, forget about it. Once again, we can come back after learning the box plot. Now, tell me, this is a marks. In this x-axis is a marks. Okay. Marks 0 to 100. This is an 100 and this is a 0 mark. Okay. Right. Now tell me, in this particular distribution, whether the students have secured the maximum marks or a lower bandwidth of a marks or a higher bandwidth of marks. This height is a frequency. This height is a frequency. Number of students. So for example, here, this many number of students has got this many marks. This number of students have got this many marks. This is the meaning here. Now, tell me from this distribution, whether the students have secured the high bandwidth of marks or a low bandwidth of marks.
High.
Low band.
High bandwidth. No, high bandwidth. See here, the marks
The
is
mode is greater. Mode is greater than mean and
Not
median.
necessarily. Don't talk about the mode and forget about all these things. Forget about all these things. Okay. Here only take the again distribution, the curve. Here the 0 mark. Here it's an 100 mark.
100 side.
See, maximum number of marks, maximum students have got the bandwidth this much. So this much, they say, for example, let us now take it as 62, then again 80 marks. Higher bandwidth, there are so many students are there. Yes or no?
Yes, sir.
Right. Now coming to this diagram, tell me whether the students has fall under the low bandwidth of marks or a high bandwidth of marks.
Low bandwidth, sir.
Low bandwidth of marks. Yeah. Whenever we are seeing the distribution curve, we have to read the data. See, it is a rightly skewed data means the most of the students has got the lower bandwidth. Negatively skewed data means the students has got a higher bandwidth of marks. What about this one?
It's equal.
Yeah. So a certain portion of the people are fall under the low bandwidth, certain people are fall under the higher bandwidth, and the middle bandwidth, the maximum number of students are fall under the middle bandwidth. Yeah. Which one always you will prefer? Whether are you preferring a low left skewed or a right skewed or a symmetric? as a good teacher, what kind of then again the distributions are, what kind of a skewness are you preferring from your
Symmetrical.
class? Symmetric. Because the deserving students should get a higher mark.
Higher marks.
The mediocre students should get a moderate marks. The poor students always supposed to get a lower bandwidth of marks. That is a good teacher's evaluation actually. And what is this one? This kind of a teacher is a what kind of a teacher? If the student, if the teacher is evaluating the marks and this distribution shows like this, what kind of a teacher? This
Strict teacher.
strict teacher. And this type of a teacher?
Lenient teacher.
Lenient teacher. That's all. From the figure, we can say that is all about inference. That is all about describing the statistics. That's all.
True.
It's not that much of a difficulty as far as the statistics is concerned. Normally, we will say, see the figure and then again tell the story. See the figure and tell the story. In Tamil, normally we will say, Padam paarthu kadai solluga. In English, I can say that see the picture and then I can tell the story. By viewing the picture, we can tell the story. That is all about statistics. That is all about statistics. Now, all of you are comfortable?
Yes, sir.
Right. Now, this is all about skewness. I'm coming to the skewness. Skewness is the measure of asymmetry of the distribution. What you are measuring? Asymmetry. If it is a symmetry, there is no skewness. If it is a symmetry, there is no skewness. If it is a asymmetry, then I can say that it is skewness. The skewness may be a positively skewed or a negatively skewed. The simple formula, there are different kind of formulas are there. What is a simple formula? The simple formula is, this is a numerator. 3 multiplied by mean minus median divided by standard deviation. This is the simplest calculation of a skewness. Sorry, now tell me, if the mean is more, what is the value of the skewness? Whether it is a positive or negative, that alone please tell me. The result is positive or negative, tell me. So mean is 100. The mean is 100. The median is 50. Tell me, what about this result? Whether the results will be fall under a negative or a positive value?
The positively skewed.
Positive, sir.
Suppose if the mean is 50, the median is 100. What is an output of the skewness?
Negative, sir.
Negative. That's all. So if the negative value indicates a negatively skewed data, if it is a positive skewness, positively skewed data. That's all. It's very simple. Rest of the things I'm leaving it to you for your own learnings. Here, my intention is make you to how to read the data and how to conclude it from this skewness. I hope all of you are comfortable with how to conclude the results from the skewness. The left skewed is a lenient teacher, right skewed is a strict teacher, and symmetric is a ideal teacher. Okay?
Yes, sir.
That's okay.
Yes, sir.
Okay. Now 7:20. Let us make a break now. Is it required or shall we continue and finish it off?
Can I see that formula once again, please?
Yeah. This is a formula.
It is
3
3
multiplied by mean minus median
okay,
divided by
and divided by standard deviation. Fine. Thank you.
Yeah. The formulas, the different kind of formulas, friends, everything is available in net or books that you can refer. But how to read it, how I am supposed to use the skewness figure, that is the learning here. That's it. Because within 2.5 hours, I can justify with this coverage only. Suppose if it is a weekly, so again it's a 15 days program or a 20 days program, then again we can talk about calculations, values, and all the nitty-gritty, then again we can talk about. But here, the time is too short. 1.5 hours, we have to learn
Formula,
the
I'm
crux.
just getting confused in this formula. That's it.
Which one?
This one.
Right. Nothing wrong. Now,
It
are
was
you clear now?
3 into
3
mean minus
into mean
median
minus
divided
median.
by standard deviation.
Yeah.
Fine.
The numerator is 3 into mean minus median. Denominator is a standard deviation.
Okay.
Shall we move further?
Yes, sir.
Right. The next one is a quartasis. Like similar to the quartasis, I am taking you to that particular diagram. Thereafter, we can come to that. The middle one, black color, is a normal curve. This is normally called as a mesoquartic. This is a normally distributed data. Suppose if the peakedness is more, it is called as a leptocortic. If the peakedness is a flat, it is a platocortic. Right. Let us now take the example of marks. Here the marks starts from 0 here, and here it's 100. Okay. Now can you describe each and every curve? Let us take first leptocortic. What kind of marks the students have got it? The majority of the students. Come on. Here is
More than a normal.
it's more than the normal. It's okay. But what else you can conclude it from this the curve?
Peak.
When the peak is increasing, what will happen? The data that it has been cluttered within the narrow range. Is it right, my dear friends?
Yes, sir.
So out of, say, for example, 60 students in the classroom, 50 students have got a mark within the range. The most of the marks, the most of the students have secured it within this bandwidth. The same thing if I am taking it here. So slightly, then again, the marks has been distributed. Here in the leptocortic, completely the marks has been distributed across the class. Few people got a bandwidth of 10 to 20, 20 to 30, few people, 30 to 40, few people, like that. So the same bandwidth of people are having a spread across the mark range. But in the leptocortic, the most of the students fall under a particular bandwidth. Okay, so more and more of a pickedness, more and more of a cluttered data. It's a cluttered means within a one particular point, then again all the students, say for example, normally when the guy is not at all reading the papers, when the teacher is evaluating, normally he tended to provide the mark 60 to 70. Always he will award 60 to 70 because he is not reading the paper. He couldn't award 90 also, he couldn't award 0 also. When he reads it, then again he can capable enough to award 0 also, 90 also, 100 also. But without reading, when he is or she is trying to evaluate the paper, he or she may tend to award marks 60 to 70. If he is awarding 60 to 70 for all the students, imagine that the marks will be 10 to leptocortic. If it's a genuine teacher, he is reading that particular papers meticulously, and deserving candidates he is awarding 100. The not deserved candidate he is awarding 0. Then it is a platocortic. It's another kind of a teacher. It's not too stringent, it's not too lenient, it's a moderate, mediocre. Then mesocortic. That is a tends to normal curve. Could you now understand? I'm with the nature of the teacher, then again I'm explaining the cortasis. Could you now get it, the points? Could you now get it, the point? Is it right? The leptocortic means more cluttered data. If it is a platocortic means more dispersed data. If it is a mesocortic means it is not too much of dispersed, it is not too much of cluttered between via media, in between that points. That is all about cortasis. That means peakedness. If the value is equal to 3, that is a mesocortic. The value is a 3, mesocortic. Okay. If the value is greater than 3, if the value is greater than 3, okay, it's called as a platocortic. Greater than 3. This is a greater than 3. It's a greater than 3. It's a less than 3. Then again leptocortic. I have given it in the slides. And now I'm coming to this one. Cortasis means heavily the tails of the distributions differ from the tails of the normal distribution. Let us take the tails. See here the tails. What is the tail of the normal distribution? What is the tail of this? Then again platocortic. The tails are differs. So the tail difference, it tends to make the distribution more cortic or a platocortic or a leptocortic. Right? All of you are comfortable now?
Yes.
Right. So in the measures, in this descriptive statistics, what we have covered so far? We have covered measures of central tendency, mean, median, mode, geometric mean, harmonic mean. Anybody can come forward to say when can you apply mean, when can you apply median, when can you apply mode and geometric mean and harmonic mean? Anyone? Come on.
So arithmetic mean is used whenever there is a summation required or summation of data is required. Median whenever the distribution is something like this, where we
Extreme
have to,
values.
yeah,
Extreme
if there is
values.
an extreme value, or maybe you need, we can say that there is a outlier, we can
Okay.
say.
Yes. Yes.
Yes. Mode whenever we have to find out the frequency of the distribution, the
Yeah.
number of
No.
times it is
Qualitative
repeating.
data. Qualitative
Yeah,
data.
the number of times it is repeating.
Okay.
Geometric, whenever there is a multiplier or we can say progression kind of a data.
Yeah. Very good. Very
And the
good.
last one, harmonic mean, whenever there are two variables and we have to find out the inverse relationship. Right.
Yeah.
Somewhere. Yeah.
Beautiful. 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 That's
Thank
all.
you.
More than sufficient. This is more than sufficient.
Thank you.
And measures of dispersion, it's a one variable, range, variance, standard deviation, coefficient of variance. And if it is a two variables are involved, covariance, and when you are standardizing, correlation. There are two measures, absolute measures, relative measures. I hope whenever you are reading the data, both you together you have to read it. Without the absence of another one, you are not supposed to read it. Don't stick with only percentage, don't stick with only absolute value. Please read both the values together so that you will get a meaningful results. Skewness means it is a how the data that is asymmetric in the distribution. So it's a positively skewed data, negatively skewed data, and symmetric data, right? Quotasis means the clutteredness of the data, pickedness of the data, or how the tails heavily distributed from the normal distribution. That is all about the quotasis. There are three types of quotasis. If the pickedness is very high, leptocortic. If the pickedness is very low, platocortic. And if it is a normal one, it's a mesocortic. Right? Now I'm moving to the next one. Before that, shall we make a break for 5 minutes? Short break?
Yes.
Right, okay. Now in my watch, okay, in my watch, the time is 7:28. Sharp by 5 minutes is more than sufficient, or 7 minutes. Let us assemble here by 7:35. 7 minutes break. 7:35 sharp, we can start the session. Time being, we can make a break.
Sure, sir.
Right. Anybody who would like to clarify the doubts? Meantime, you can clarify the doubts also. Right? I'm free to answer.
So for, excuse me.
Yeah.
So for mean, there is no requirement of any qualitative data, no? For mean.
For a mean, you can't, for a qualitative data, you can't apply mean, sir.
Okay, okay.
Say, for example, male, female. When you are interested to talk about a male, female, we can't add and subtract. Any values that you can't be arithmetically processed, adding, subtraction, multiplication, division, sir. Only then again, we have to go ahead with the counting.
Okay.
And more number of times, if it appears, that's called as a mode.
Okay.
And tomorrow we are having a topic called as a scales of measurement, sir. After learning the scales of measurement, even better understanding you will get it.
Okay. Thank you, sir.
Thank
Thank
you.
you.
Let us now start. Now let us start with the third topic, exploring data. It's very, very important. It's like seeing the figure and telling the story about the data. Normally, whenever we are starting the research work or whenever we are collecting the data, as soon as the data that it has been collected, first we have to start to visualize with the graphical representation. That it will give a great insight, and after getting an insight from that particular data, we have to go ahead further, dive into that particular statistical analysis. That is why it is called as exploring data. Exploring data. Okay. Right. Let us now start. There are different kind of pictorial representations are there. I am picking up a few selected pictorial representation and how to represent and on what context we have to use that particular representations. I will explain. Okay. Right. My window is visible now. Can you confirm?
Yes, sir.
So the first and foremost in the exploring data, it's a mean plot. From the name itself, you can understand. Already we have learned about mean. Mean is nothing but simple average. Right. The purpose of this particular graphical presentation is to identify the location. Here, this word is very, very important. Locations. Here, I'm interested in locations. I'm interested in location. I'm interested in location. That is very, very important. Locations only I'm interested in. Location between the groups. In the vertical axis, I'm taking the group mean. In the horizontal axis, this means this is a y-axis and this is an x-axis. I'm taking the group identifier. The reference line is plotted at the overall mean. See here, I will showcase this one. This solid line is called as a overall mean. The solid line is a overall mean. Overall mean. The solid line is a overall mean. Okay. And this is the mean. This into mark is the mean of the first month. This is a mean of the second month, mean of the third month, mean of the fourth month, mean of the fifth month. All the 12 months mean. This is an overall mean. All the 12 months data, when you are combining together and you are calculating it, this is around 1.185. This is 185. Okay, right. From this figure, can you say that month after month, you are, let us take, this is a mean rank or it's a sales value or whatever may be. Please take up. What happens, what tends, and what is the trend? What is the pattern that it happens? Can you say, my dear friends, come on. Month after month, what happens? Say, let us take this is a sales value. Imagine this is a sales value. Month after month, whether the sales value, what happens to the sales value?
It's declining, sir.
Yeah, it's very declining. It's very simple, mean all. The location has been sifted. The locations has been sifted. Sifted from 205 to what? 135. Drastically that it has been sifted. The locations has been. Location means it's nothing but it's a mean value. Okay, so by plotting this figure, you can conclude the movement of the data across the time period. Not necessarily across the time period. Anything, then again, you can take it in x-axis. Clearly that it will communicate. That is a purpose. Yeah. Right. See, what are the questions you can ask it from that particular mean plot? The first questions you can ask is, the mean plot can be used to answer the following questions. The first one is, are there any shifts in the location? Is there any shift in the location?
Yes, sir.
Yes. What about the second one? What is the magnitude of the shifts in the location? Whether the magnitude is very high or very low or moderate. Shift in the location. Or
High,
in the sales.
high, low, moderate.
High, low, moderate in general. Across the 12 months. From first month to 12th month. Whether the locations has been drastically shifted or it's a moderately shifted.
In general, it is fine, but between 6 to 7, it is extremely.
aggregated.
Right, okay, don't bother about the individual data.
Right.
Take it the first and then again take it the second. The shift in the location is a magnitude wise, it's a drastic or it's a light or
Drastic.
moderate. Drastic, that's all. See here, the magnitude of the shift. Then again, is there any shift in the location? What is the magnitude of the shift? Then next one is a pattern. What is a pattern? Yes, there is a shift in the location. There is a high magnitude, whether it's an upward or a downward. Downward. So there are three questions can be answered with the help of the mean plot. Whether there is a shift in the location, what is the magnitude of the location, what is the magnitude of the shift in the location, and what is the pattern or what is the distinct pattern of the shift in the location. There are three questions that can be answered with the help of the mean plot. Is it very clear now?
Yes, sir. Yes, sir.
Right. So the second one is the standard deviation plot. Now I am coming to the standard deviation plot straight away. Thereafter, I will come to the explanation. See here, in the x-axis, we are taking the month. In the y-axis, we are taking the standard deviation. Okay, standard deviation. Standard deviation of anything, any products, imagine, right? So the small into marks are all individual observations. See the first month standard deviation, second month standard deviation, third month, fourth month like. And the solid line is overall standard deviation. The solid line is a overall standard deviation. OS, overall standard deviation. Okay. Now, can you read this particular plot? That it talks about the dispersion, not the mean value, dispersion. That talks about the dispersion, right? What is the purpose here? That it detects the changes in the scale between the groups. Okay. And the standard deviation plots are normally we are framing by in the vertical axis, we are taking the standard deviation and we are taking the y-axis, we are taking the group identifier. Here the group identifier is a month and here that is a measurement of the product. So the reference line plotted overall standard deviation, that is the overall deviation we have done it. Right. Now the question here, are there any shift in the variation? Okay. Or what is the magnitude of the shift in the variation? And what is the distinct pattern? Similarly, there we have talked about the location, but here we are talking about a dispersion. Okay, right. Now tell me from this figure, what happens? Whether there is a shift in the dispersion?
Yes.
Yes. What is the magnitude?
Drastic.
Drastic. And what is there any distinct pattern?
Yes, sir.
Yes.
Kind of an oval curve, kind of
Yeah. Then again, see here, up to the month 7, the dispersions keep on increasing
Upward.
and thereafter keep on
Decreasing.
declining. See, initially the dispersion is increasing and thereafter that starts to declining. See, there are 3 questions. Is there any shift in the variation? Yes, there is a shift in the variation. Okay, right. See, instead of this particular diagram, okay, let us take a small diagram here. And this is a standard deviation. The standard deviations are look like this. The standard deviations are look like this. Can you say that there is a shift in the dispersion?
No, sir.
No, because it's too closer to the overall standard deviation. Very too closer to the standard. There is no shift. There is no magnitude change. There is no pattern. Okay, but here, yes, there is a shift, upward shift. Then afterwards, downward shift. The magnitude is drastic. Then again, the pattern is initially it's an upward, thereafter it's a declining. So there are 3 things. Then again, I'm revealing it from this particular pictorial representation. So what actually you have to do is you have to calculate a standard deviation for each and every month that it has to be plotted. And all the 12 months, the data has to be grouped together and you have to calculate the overall standard deviation and that it has to be plotted. Nowadays, the softwares are available and whenever you are clicking the standard deviation plot, that it will throw the standard deviation plot provided if you are feeding the data. Manually, there is no need to calculate. But how to interpret the graph? While you are interpreting the graph, you have to talk about whether there is a shift in the variations, whether there is a magnitude. What is the magnitude of the variations? What is the pattern, distinct pattern in the shift of the variations? In these three dimensions, you have to talk. Are you comfortable?
Yes, sir.
Right.
So,
If you are comfortable, shall we move to the next one?
Yes.
Right.
yes, sir.
Next one is a box plot. This box plot is a one that it accommodate both location as well as variations. Both that it accommodates. It's a very, 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 very important tool in the statistical analysis. The box plot, it's again the name, from the name we can understand the box kind of a pictorial representation. That is a very important tool in exploring data analysis. Exploring data analysis tool, in that it's a very important graphical presentation. In the box plot, in the vertical axis, we are putting the response variable. In the horizontal axis, we are putting the factor of interest. Sir, what do you mean by response variable? What do you mean by factor of interest? Let us explore with the small examples. Okay, I'm taking you to the graphical presentation. Say this is a box plot. The box plot contains Q1, this is a quartile 1, this is a median, quartile 3, and this is a minimum, and this is a maximum. Or sometimes it is not a minimum or a maximum, it is a Q2 minus Q1, okay, multiplied by, okay, multiplied by inter 1.5 times interquartile range, okay, interquartile range. Or time being, please forget about it, take it only the maximum is in the right hand side, minimum in the left hand side. This is a box, it's like a rectangular box. The starting of the box is a Q1, the ending of the box is a Q3, and this is a median, and this black color is called as a whisker. This is a left side whisker, this is a right side whisker, and this is called as a box. See, in this, from minimum to Q1, 25% of the data lies. In Q1 to median, 25% of the data that it lies. In median to Q3, 25% of the data that it lies. In Q3 to maximum, 25% of the data. Say, for example, you are having 1,000 data sets. In that, out of 1,000 data sets, how many data sets that it will fall between minimum to Q1? 250 data sets that falls within this particular range. Okay. What about the Q1 and Q2? This is called as a Q2. Median is nothing but it's a Q2. How many data sets that it lies? 25% of the data sets. What is the N? The N is 1,000. Okay, imagine 1,000. If it is 1,000, how many data sets that it will fall between Q1 and Q2? 250 data sets fall into this box. And from Q2 to Q3, another 250 data sets. And Q3 to Q maximum, 250 data sets. Okay? Can you now understand?
Yes, sir.
The box plot is
Yes, sir.
nothing but that it contains 5 number summary. Minimum, Q1, Q2, Q3, maximum. Q1 is a lower quartile, Q3 is an upper quartile, this is a middle is a median, and then again left hand side is a minimum. From minimum to Q1 is called as a whisker, and Q3 to maximum is called as a whisker. In between Q1 and Q3 is a box, rectangular box. That is why it is called as a box and whisker plot. Box plot, or alternatively it's called as a box and whisker plot. Box and whisker plot. Okay. And 25% of the data, Number of data only, not the value. 25% of the out of 1,000 data sets, 250 data sets lies between minimum and Q1. Q1 to Q2, another 250 data sets out of 1,000 data sets. Suppose if it is in 100 means, how many data sets? 25 data sets. Here it's a 25 data sets. Here 25 data. Here 25 data. So from Q3 to maximum 25, medium to Q3 25, Q1 to medium 25, minimum to Q1 25 data sets. That lies. This is a basic idea. Further, we can dive in detail about that particular box and whisker plot. Now tell me, come on, are you comfortable with the box and whisker plot? What are the five components of the box and whisker plot?
So the minimum,
Minimum,
Q1, Q2 or the median,
yeah,
Q3 and maximum.
that's all. With that, then again we are picturizing the data set, right? Coming to this, now I am associating it with a box plot with left skewed data, right skewed data, and symmetric data. If it is a symmetric data, please see the whiskers are too lengthy. It's more than the box size. The box is like equally distributed. Both Q1, this is a Q1, this is a Q2, and this is a Q3. Equally distributed. The box is equally distributed. Okay, and both the whiskers are also equally distributed. See here, can you see the length of this whisker, lower whisker, this length of the upper whisker, both are equal. One Q1 and Q2 box size, Q2, Q3 box size are similar. This will tend to symmetric data, normal data. Suppose if it is a left skewed data, the left hand side whisker is too lengthy than the right hand side whisker. Okay. And also, please see the Q1 and Q2, the Q1, Q2 size of the box, and Q2, Q3 the size of the box. See here, what is the size of the box? See here, this is a left skewed data. If it is a right skewed data, Q2 to Q3, the box is very high, or the box is very big, and the whisker, upper whisker is too lengthy than the lower whisker. Can you understand now? Can you observe the difference?
Yes, sir.
Because the system will throw the box plots. Sir, how can I draw? Yes, learning how to draw, it's required. Please leisurely do it. But how to read, how to interpret, that is very, very important. So for constructing a box plot, what are the components are required? Minimum, Q1, Q2, Q3, maximum. 5 values are required. If both the whiskers are similar, if both the Q1 and Q2 size box and Q2, Q3 size box are similar, then that it's tend to normally distributed data. If the right hand side whisker is too lengthy and the Q2, Q3 box is too large, then it's a rightly skewed data. If the left hand side, that is a box Q1 and Q2, it's a bigger size, and the lower whisker is a bigger size, then it's a left skewed data. Now I am stopping my lecture. Please tell me if you are comfortable, or otherwise ask questions. I will clarify my doubts. I will clarify your doubts. Yes, guys?
So concept-wise, it's clear.
Yeah. How to
Could you give any
construct?
example, or could you practical application of this?
1 minute, I will showcase to you.
Yes, sir.
This is a small restaurant case analysis. Okay, let us take this one. It's very interesting. It's a day-wise sales that it has been given, my dear friends. In the x-axis, sales value has been given. In the y-axis, it's a days. Each day, I have constructed a box plot. Okay, right. Now, tell me, in which day the sales is very high, in which day the sales is distributed very highly. Here we have to talk about two things: location, dispersion. Location means mean value. Dispersion means standard deviations. Is it right, my dear friends? In which day the dispersion is very high, in which day the dispersion is very low, and in which day the mean sales value is very high, in mean sales value is very low, in which day? Come on, compare and tell me. Sunday, Monday, this is a Tuesday, Wednesday, Thursday, Friday, Saturday. This is a restaurant sales from February 2016 to January 2017. Come on. Can you see this one? Can you now conclude whether it's a left skewed data, right skewed data, symmetric data? First, let us apply here. In which day? In which day it's a symmetric? In which day is it symmetric?
Wednesday.
So Wednesday.
Yeah, that's all. It's very easy. It's very easy. Approximately, I can say that Wednesday is normally distributed. Approximately, I can say. In which day it's a negative, that is a positively skewed, highly positively skewed.
So Sunday.
Sunday, highly positively skewed.
Monday.
But Monday is a highly positively skewed. Is it right? Then again, which day negatively skewed? Any day negatively skewed? No.
No.
No,
No,
there's no
sir.
negatively skewed data, only positively skewed data. Okay, right? See, such a kind of an inference. See, this is another one more practical example, meals analysis of the restaurant. Normal day meals. This is a normal day. And this is a Valarpirai Mugurtam. And this is a Teipirai Mugurtam. There are two Mugurtam in the marriage. When the full moon, the marriage that will fall during the full moon time, the marriage falls during the new moon time. They are suspecting that the sale is different. Now tell me, except this normal day, in the Muhurtam days, in the marriage days, whether the Valaripare Muhurtam is having a more dispersion or the non-Valaripare Muhurtam is a more dispersion. Or what kind of a distribution? Come on, tell me. Let us take a non-Valaripare Muhurtam, whether it's a positively skewed data or a negatively skewed data.
It is positively skewed, sir.
It is a positively skewed. This one?
Negative.
Yeah, that's all. This is a very informative, and based on that, I can decide, I can plan my meals preparations in the hotel. I can plan. See, in the Valarpare Muhurtam, most of the times the sales is very high. In the Teipare Muhurtam, most of the times then again the sales is less. Okay, the sales is less. Most of the time, the sales is less. At some of the non-Teipare Muhurtam only the sales is more, tends towards more maximum meal. So, see, this is a basic exploring data. Further, I have to dive into the deep. Is it right? That it does not give the complete inputs for my decision-making process. Initially, when I'm trying to explore the data, that gives an input for me. Okay, right. Now tell me whether the normal day is normally distributed or it's a skewed data. Normal meals days. Normal meals days. This is a normal day.
Normal.
Normal day.
Normal, sir.
Yeah, this is normally distributed. Is it right? See, this is the best example that again I can quote from the practical. This is a live data actually. This is a live data with which then again we have explored it. This is the number of meals I have mentioned in the x-axis, and the y-axis is a factor I'm concerned about it. Okay. The factor means here the Valaripare Muhurtam, Teipare Muhurtam, non-Teipare Muhurtam, like that again. Here the days of the week. Sunday, Monday, Tuesday, Wednesday, Thursday, Friday. Right, okay. Now, from this figure, can you quickly conclude in which day I have to prepare more food? Or otherwise, can you say that in which day the sales is less, in which day the sales is more? Among the 7 days, in which day the sales is low, in which day the sales is very high? Come on, tell me. Take it down the median value. Take it on the median value and see and compare and tell me in which day the sales is low and which day the sales is very high. Can you understand my question?
Sunny.
Hello?
No.
Hello? Come on.
Yes, sir. We're able to hear you.
In which day the sales is very low? Among the 7 days, in which day the sales is very low?
I feel the sales is low on Tuesday.
Yeah, super. Then next one, in which day the sales is very high?
Monday.
Monday, sir.
Monday.
Monday is the maximum sales, even though this is a Q2. Where is a Q2 here?
Sunday. Sunday.
Yeah,
Sunday,
Sunday.
I meant.
Sunday.
Yeah.
That's all. It's like a horoscope. By seeing the horoscope, then again telling your future, your past. Like then again, we can talk about the sales of the restaurant. Oh, Sunday is the sales is very high, and Tuesday. See one more pattern. Can you observe the one more pattern? The Sunday sales is very peak. Slowly, that's coming down Monday, and that it's tipping the way lowest sales in Tuesday, and thereafter slowly that's picking up. Wednesday that it goes up. Thursday is slightly moderate, and Friday, Saturday, then again touches Sunday, it's a peak. See, Sunday, from Tuesday onward, the sales picks up, and Monday that it reaches the peak, and then afterwards that it's slow down. So Monday, it's dipping again, it's coming down towards Tuesday, then again slowly that's picking up. Wednesday, Thursday, Friday, Saturday, like then again that touches the Sunday. Can you now understand? Is that so?
Yes, sir.
From this figure, my dear friends, you can answer these questions. The box plot can provide an answer to the following questions. Whether the factor is significant in this one, what is the factor? Valarippurai Muhurtham day sales, non-Valarippurai Muhurtham day sales, normal day sales. This is a factor. Whether the factor is matters here?
Yes, sir.
Yes. This is an answer for this question. Does the location differ between the subgroups? The location differs from the subgroups?
Yes.
Yes, right. Then, does the variation differs between the subgroups? In which day the dispersion is very high? During the Muhurtham days, dispersion is very high compared to the normal day sales. The normal day sales dispersion is very low.
Yes, sir.
So the meal ranges from 250 to 450, the oscillation. But here, see the oscillation. This is nearly 375. This is nearly 375. 375 to 1100. See how much the dispersion. Some of the Muhurtham days only 375. Some of the Muhurtham say it's 1100. See, the oscillation is too high in the Muhurtham days than the normal day meal. Can you now say variation differs between the subgroups?
Yes, sir.
Then finally, that it also explore whether there is an outliers. The outliers for that normally, my dear friends, what we are trying to do is we are using the interquartile range. See in this graph, this is an outliers. This is an outlier, and these are all the outliers. Okay, right. So in the x-axis, I am taking the mission 1, mission 2, mission 3, mission 4, and this is an energy consumption of the energy. Can you now say that which mission is a better in energy consumption? Which machine is a better in energy consumption? Which machine is more vulnerable? Which machine is a more amicable as far as the energy consumption is concerned? Come on, comparing these 4 diagrams, tell me. Right now, tell me which machine is consuming more energy? Either 1 or 2 or 3 or 4?
3.
Pardon?
3.
3. Ah, very good. 3. This is a median.
Yes.
And this is a median. And this is a median. And this is a median. See here. Which machine that it consumes more energy? Machine 3. Yeah, obviously. Which machine consumes very low? Machine 1.
Machine 1.
And machine 2, comparatively speaking, 1 and 4, the machine 2 is consuming a little bit more energy. Like by seeing the graph, we can talk about it. We can talk about the location, we can talk about the dispersion, we can talk about the outliers. So that is the one that again that it has been showcased here. See here, the box plot that it talks about whether the factors are significant. Here, what is the factors that is significant? What is the factor is significant? Whether the machines are significant in terms of energy, whether the machine is significant. Is it significant or not significant? Or whether there is a significant difference there or not?
It is.
Yes, sir.
Is there is a significant difference among the machine as far as the energy consumption is concerned?
Yes, sir.
Okay. Like similarly, I can say that here, whether there is a significant difference in the average sales across the days.
Yes, sir.
Yes. So these are all the questions. Whether the factor significant, whether the days of the sales significant, whether the machines are significant. Yes. Whether the locations differ across the subgroups, whether the variation differs across the subgroups. Is there any outliers? So all the 4 questions can be answered with the help of the box plot. So the mean plot talks about the location. The standard deviation plot talks about the dispersion.
Hello.
Okay. Is it okay?
So your voice was not audible in between.
We lost your voice for a few seconds, sir.
Right. Okay. Now, are you now? Can you able to answer these 4 questions?
Yes, sir.
Whether the factor is significant, whether the location is different among the subgroups, whether the variations differs between the groups, whether is there any outliers? Okay.
Yes, sir.
Right. Now, this is a one. Instead of a minimum, here we are taking Q1 minus 1.5 times interquartile range. Interquartile range means nothing but Q3 minus Q1 is called as interquartile range. IQR means Q3 minus Q1. This Q3 minus Q1 interquartile range multiplied by 1.5 times of the interquartile range, you have to subtract from the Q1. 1.5 times of the interquartile range you have to add with the Q3 to fix the upper boundary, lower boundary. Below the lower boundary, if the data lies, say this is a one, this is an outliers, and this is a round circles are outliers. So this is an upper boundary, lower boundary is fixed by Q1 minus 1.5 times interquartile range, Q3 plus 1.5 times interquartile range. That it gives me the upper boundary, lower boundary. Beyond that boundary, is there any data point lies, that is called as an outliers. Always we have to knock off the outliers from our study. Are you comfortable?
Yes, sir.
Right. That outer, see here, this is equivalent to what, my dear friends? It's equivalent to 3 sigma. Here also equal to 3 sigma. Upper 1.5 times interquartile range when you are considering it to subtract from Q1, and when you are adding the 1.5 times interquartile range with the Q3, the upper boundary, lower boundary covers plus or minus 3 sigma data range. I have depicted with the normal curve. I depicted with the normal curve. Okay? Clear now? Is there no? Any
Somebody is
doubts?
asking to repeat.
Yeah. See, when I'm talking about the basics of one, here we have talked about minimum, maximum. This is a basic understanding for which I have stated is a minimum maximum. But actually, what we are trying to do is the lower boundary. This is called as a lower bound. This is called as an upper bound. The lower bound will be calculated by Q1 minus 1.5 times interquartile range. The upper boundary will be calculated by Q3 plus 1.5 times interquartile range. Beyond this upper boundary and lower boundary, the data point lies. Say, for example, a data that it lies here. The data that it lies here. From your data sets, the data lies here. Imagine. The data that lies here, it's an outlier. The data that it lies here, it's an outlier. And it has been shown here. Can you see? These two data points are outlier. These two data points are outlier. Are you comfortable now?
Yes, sir.
Right. Okay. So please wander over. Take the same figure, visualize, try to interpret. Because in this particular class, just you can smell or you can observe, right? Okay, something in such a way, then again I can identify the outlier. Then again, you have to put your heart and you have to interpret it, and you have to, by words, then again you have to utter the concepts. And then only, then again you can try to understand actually. Okay. Now I am coming to the scatter plot. Scatter plot is a one that it will help me to plot the figures or plot the data points when I am having a two numeric data. In the box plot, see here, in the box plot, see here in the x-axis, see here, this particular y-axis, I put this is a categorical variable. Sunday, Monday, Tuesday, these are all categorical variables or qualitative data. These are all qualitative data. And the sales is a numeric data. Sales is a numeric data. So one categorical data, one numeric data here. But here, both are numeric data. Scatter plot. When you are having a two numeric data, you have to apply scatter plot. Scatter plot. Okay. The scatter plot is a one that it will help us to know whether the two variables are correlated or not correlated. Whether it is a positive correlation or a negative correlation. Okay. Clear now?
Yes,
This
sir.
particular data, approximately I can say that negatively correlated. Moderately negatively correlated. These two data sets are. Like by seeing that one, then again easily we can understand. Okay. Right. The next diagram is called as a dot scale diagram. The dot scale diagram is a one that it will help us to identify the outliers. See, again, with the help of the software, we can draw this dot scale diagram. The dot scale diagram, see here, the dark green color. The dark green color is nothing but first quartile, third quartile. The median is then again this one. The red color is a mean value. Is it right? And all the dots are individual data points. And the yellow color, this is a 1 sigma. This is a 1 sigma, this is a 2 sigma, and this is a 3 sigma. Okay. Suppose the data point that it lies here, imagine. Beyond 3 sigma, this is an outlier. Okay, so this particular diagram will help us whether the data that it lies within 2 sigma or a 3 sigma, or is there any outliers or not. It's a substitute of like a box plot. Okay, what is a box plot here we have seen? The same thing here also. This is an alternative diagram. It's a dot scale diagram with which we can find out the outliers. Say, as soon as we are collecting the data, we have to put it in a dot scale diagram and we have to see whether the collected data sets that fall under 2 sigma level or a 3 sigma level or a 1 sigma level. If it is a 1 sigma level, more cluttered data. If it is a 2 sigma level, moderately dispersed data. If it is a 3 sigma, it's a normally dispersed data. Normally dispersed data. Okay. It's a peakedness. If it is a 1 sigma, peakedness is very high. If it is a moderate peakedness, this is a normal peakedness. Peakedness means quartiles. Already we have learned about it. Okay. Are you comfortable with this dot scale diagram? In the dot scale diagram also, we are taking first quartile, third quartile, meaning Q1, Q2, Q3, and mean, and as well as a 1 standard deviation, 2 standard deviation, 3 standard deviation, and all other things. Okay. The two dark greens, this is a Q1 actually, this is a Q1 and this is a Q3 and this is a Q2. Okay, red color is a mean value and this is a 1 sigma, this is a 2 sigma, yellow color, this is a 3 sigma. Okay, are you comfortable? This is especially to identify the outliers. Data outliers. Okay?
Yes, sir.
Right, okay. Now this is an histogram. Histogram, when you are having a numeric data and when you are binning or when you are making it as a frequency table, at the time you can apply histogram with the curve fitting. That it will tell whether the data is positively skewed or negatively skewed, like then again that it will clearly tell. Can you tell me whether these two data are negatively skewed or positively skewed? You have to take the range of this value also. Take the range of this value. Okay? Come on, tell me.
Negatively skewed.
So already I hope you may aware about it. And this is one example of a bar and line chart. So one variable I can use the line chart, one variable I can use it for a bar chart. See, for a sales, I'm using a bar chart. For a line, I'm using a percentage of the sales. The percentage of the sales is a secondary axis. The sales value is a primary axis with which I'm constructing a figure that it will give a complete picture about the sales trend. Sales trend of the department. In which department the sales percentage is very high? Among the 5 departments, which department?
Department D.
Which department the sales is very low?
A department.
Yeah, that's all. So these are all some of the visualizations. See, even if a raw data, when you are having it or in the tabulated values, you couldn't come to a conclusions quickly. By seeing things, then again, immediately we may come to a conclusions. Okay. So this is an example of a bar and line chart. And another chart is called as a Pareto chart. This is called as a 80-20 principle. I hope all of you may comfortable with that principle, 80-20 principle. The Pareto, then again, he identified it. The 80% of the wealth of the world is lying with the 20% of the people in the world. That is the origination of the 80-20 principle. The 80-20 principle is applicable in our life extremely. Even say, this is one of the example, the State Bank of India has conducted a research work. And they have identified what are all the causes that it makes the people dissatisfied. See, from this graph, I can say that 80% of the issues is because of the 2 reasons. See here, wrapped card is jammed in the ATM, card unreadable. These 2 issues count for how much percentage of the issues? How much percentage of the issues? Because of 83%. The remaining 17% of the problem, remaining 17% of the problem because of ATM malfunction, ATM out of cash, wrong keystroke, invalid amount requested, lack of funds in the account. See, these are all, how many issues are there? This is a 1, 2, 3, 4, 5, 6, 7 issues are taken. Suppose if the SBI would like to address the issue, which two issues has to be addressed immediately?
The first and second.
If they are addressing the first 2 issues, how much percentage of the issues they can solve?
83%.
Solve. That's all. It's an applicable for sales, applicable for production, applicable for personal life. Everywhere you can apply 80-20 principle. So even if you are a teacher, you can encourage the students to apply 80-20 principle to explore what is the 80% of the causes because of that particular, then again, issues or the reasons. Like the 2 reasons that it causes 83% of the issues. Okay, sir. Like this is normally called as an augue curve. OGIDE, augue curve. This is a cumulative. The line chart. It's a cumulative percentage. See here, this is a cumulative percentage. And when the line chart consists of a cumulative percentage, it's called cumulative, not percentage, cumulative values. Cumulative percentage or cumulative value. It is called as an augue curve. OGIDE, augue curve. Augue curve. Cumulative augue curve. Cumulative augue curve. And this is a base of the 80-20% pictorial presentation. Okay. This is called as a Pareto chart also. Sales bin value. Another example that again I have put in. This is called as a Pareto chart. And this is another example I have done it. Okay. Now time is exactly 8:22. We finished the 3rd topic, exploring data. Okay. Don't think that it's completely I have exhausted. No. Just then again, I have started with a few important pictorial representations or graphical presentation of the data. With the help of that, we can explore the data. There are n number of charts are there. Don't think that this is the only set of charts. And within the given time, then again, I covered it. In that, any doubts or any clarifications are there, please ask me. The last then again, couple of minutes, then again, I'm allotting for discussion. Clarification of doubts, discussions, or anything. Or even from your own research work, you can raise some of the questions, whatever, relevant to these topics. Suppose if you are having other things, then after 8:30, I will respond to you. Okay, right, come on. Now it's a time for interactions. Whatever may be the doubts, please ask me. Sir, I have, Madam, thank you for Priyadarshana. What is the name? I have Krishna. Priyadarshana Krishna. My pronunciation is right? Yeah. Krishna. Thank you for your comments, sir. I picked the concepts in such a way that where you will struggle. Okay, that may be a bitten pieces, but when you are diving into that research work, all these inputs will be handy. Okay, right. Any doubts or any clarifications? Last 5 minutes is there.
No, sir, no doubts. But I have also commented, but I wanted to ask that do you take presentations on softwares and non-parametric data or maybe econometrics also?
Pardon, once again, what is your question? Sorry, I couldn't get it.
Yeah, I'm saying that it's not a question actually, but I've also shared a comment. So first of all, I would like to compliment you on your presentation and presentation skills. The entire PPT was very clear. And I was asking if you organize other kind of presentations on non-parametric data especially, or econometrics.
Not econometrics, madam. I am taking the basic statistics applications.
No. I am asking you.
I'm saying.
Okay.
I think you are asking the coming forth. That is tomorrow's sessions. Are you asking about it?
No, I'm just asking you generally that
General. No, I'm not that much well versed in econometrics
Okay,
tools,
okay.
but I'm comfortable. But my
Okay.
core area is a multivariate analysis.
Okay.
Multivariate analysis.
Okay.
And especially data handling, cleaning process, analytics part. My strength is in analytics part.
Okay.
Right. Okay.
Thank you, sir.
If you are asking, madam, then again, I can cover the entire, then again, parametric and non-parametric test as well as a multivariate analysis like a cluster and joint, and then again in the factor analysis, principal component analysis, confirmatory factor analysis, like all these areas, then again comfortably, even including logistic regression. Then again, all these areas I'm much comfortable. Then again, I can support you.
Okay. Thank you, sir.
Thank you.
So, okay.
Any doubts regarding this basics and this sampling distribution, central limit theorem, and then again measures of central tendency, dispersion, skewness, kurtosis, then followed by then again mean plot, standard deviation plot, and box plot, box and whisker plot, then again scatter plot, then again dot scale diagram and Pareto chart, bar and line chart. Right. As we
No
expected,
questions,
there
sir.
again, pardon, madam?
No questions, sir. Thank you.
Thank you, madam. I'm very happy to present sharing my knowledge with you as a teacher community. I think most of you may be a teacher and as well as students and other corporate world also the participants may be. Anyhow, then again, I'm delighted to share my learnings and where I struggled, where I stumbled down, and all these concepts. Then again, I picked it, and then again, I have collated and I have made a presentation here. That may be a bit and pieces, and probably somebody may disappointed, may have a disappointment because it's a bit and pieces. But anyhow, then again, whatever your requirements or whatever your inputs is required, please ask me. Then again, I will fulfill. Okay, in tomorrow class, is there anything else has to be covered? Please tell me well in advance, I will cover it. So tomorrow, what we are planning is to cover the scales of measurements. Scales of measurements. Tomorrow's sessions, we are talking about scales of measurements. Very, 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 very important. Because whenever we are talking about data collection, first we should have a clarity about nominal, ordinal, interval, and scale ratio data, and followed by sampling techniques, and followed by inferential statistics, the context in which test I am supposed to choose. Here, the learning part is not learning how to conduct a t-test, how to conduct a z-test. Here, I am trying to teach you which test I am supposed to choose. Whether I am supposed to choose an ANOVA, whether I am supposed to choose a two-way t-test or a one-way t-test or an independent sample t-test. Like, then again, which test I'm supposed to choose it? What is an equivalent non-parametric test? All these things tomorrow we may cover it. Okay, this is our next day, tomorrow's schedule. And with that, then again, I'm concluding my session. Datta sir?
Sir?
Madam, tell me, madam.
I have a request. While you are now talking to us, I think most of us are able to grasp the concepts. We are able to understand. But in order to remember it better, it would be really wonderful if we can have the slides or if
Sure,
we have
madam.
the recorded
Sure.
session sent across to us.
Recorded sessions will be shared by Datta sir. Don't worry, I will share the PPT and Shar will share it to you.
Thank you so much, sir, because I'm sure that when we go back to this content a little later, I don't want us to feel like what we had done on that day. So just wanted to ask you.
I will share the PPT. Entire PPT, I will share it to you. Don't worry.
Thank you so much, sir. Truly appreciate your inputs today.
Thank you.
Thank you, sir. Thank you so much. So we have come to the end of the day one session. Once again, on behalf of MTC Global family, I extend my heartfelt thanks to all the participants for their active participation, and the resource person and the mentor or the facilitator, whatever name we call him, Dr. Murugappan sir, for sparing his valuable time and taking us all through for last 2.5 hours journey into through the contents of day one. As per we discussed. Thank you, sir. So look forward for tomorrow's session, and definitely as Divyasri ma'am asked about the video. It will be uploaded by tonight itself. So I'll share the link. It will be uploaded in our MTC Global Headquarter YouTube channel, and we have huge followers over there. So I'll post the link in our WhatsApp group. So kindly please go through it, and sir will share the PPT. Thank you once again, sir, and
Thank you, sir. Thank you very
look
much.
forward for tomorrow's session. Thank you,
Thank you, sir.
and good night to all of you. Thank you so much.
Thank you. Thank you. Good night to everybody.
Thank you, Datta sir.